Hello students, this is Professor Chalai, and in this video we're going to look at valence-shell electron-pair repulsion theory, or VSEPR theory. As always, you can follow along with our Chapter 7 workbook. By the end of this video, you should be able to predict the shapes of small molecules using this theory. Let's get started. Okay, so what is VSEPR theory? Well, as the name suggests, and as scientists, we don't like to name things very complicatedly. It's basically the repulsion between various electron pairs in the valence shell that determines the geometry of a molecule. For example, let's start with a simple molecule of carbon dioxide, right? We know carbon dioxide forms double bonds, right? And then there's lone pairs over here. Whenever we're looking at the geometry of the molecule, we look at this central atom here that connects the other atoms in this molecule, and we try to look at how many different groups of electrons there are around this atom. And here we see that there's 2 bonds here and 2 bonds here. There are 2 electrons in each of the bonds, so there's 4 electrons here and 4 electrons here. Because electrons are negatively charged, they're going to try to repel each other. And so this set of electrons are going to try to repel that set of electrons as much as possible. So if I had drawn carbon dioxide like this, for example, as instead of in a straight line, we know that this might not be likely because this pair of electrons or that double bond will try to repel that double bond as much as possible, pushing them away from each other as much as possible. That's the idea behind valence-shell electron-pair repulsion theory. The electrons in the valence orbitals, which as we know are either responsible for the bonding or, let's use a different color, or the lone pairs, those are all the valence electrons, and they will try to repel each other as much as possible. This is where Lewis structures come in very useful. If we're able to draw proper Lewis structures, we can help very easily predict shapes of some molecules. So let's look at what these shapes might be. And here, there's an entire table giving us the shapes of the electron geometry or of the molecule, and then the angles between the different bonds. So here, in this example, the bond angle will be 180 degrees. If it's anything less than 180 degrees, they'll try to push each other away. So in that example, we had 2 electron groups for carbon dioxide. Why 2 electron groups? This collection of bond here is a single group, so that's one group. And this set of electrons over here in this bond is one group. So there's 2 groups, and so with 2 groups, both of them are bonding, we have what we call a linear geometry. So the electrons will form a linear geometry and the molecules would be linear. Linear just means in a straight line, so we have 180 degrees. So you might think, well, when you have 2 groups, the situation is simple. What happens if you have 3 groups? Well, let's look at that. So this is a little simulation that sort of predicts what happens to the electrons when you put more groups around an atom. So we just talked about if you have 2 groups, they'll try to repel each other so that they're completely opposite each other. So they'll always form a straight line, right? There we go. If you have 3 groups, they'll repel each other and they'll form this flat structure where the 3 groups are sort of equidistant. They're separated by 6 degrees, 60? 6 degrees 18, 120 degrees, sorry, from each other. We call this sort of geometry here trigonal planar, right? So if you have 3 electron groups, the electrons are going to be in this trigonal planar geometry. But those are for electron groups. What about the bonding groups? Right, so let's say we remove one of these electrons and replace them with a bond, right? We just get, well, that's not very interesting. Let's remove 2 of the groups and replace them with 2 bonds. We get this sort of bent geometry, right? So if we had 2 bonds for the 3 electron groups, we have a bent geometry. The angle would be close to 120, slightly less. And then if we had 3 electron groups and through all of them are bonds, we'll have the trigonal planar geometry like this. All of them 120 degrees. So let me just clarify that by electron groups, we mean all bonds, and all lone pairs, right? Every lone pair is a one electron group, and every bond, whether it's single, double, or triple, is already is one electron group. So in the case of 3 electron groups, if all 3 are bonds, we have this geometry here where it's flat, so we'll call it planar, and it's 3-sided. It looks like a triangle, so we'll call it trigonal. So we will call this molecule trigonal planar. If we replace one of those bond with instead a lone pair, there's still 3 electron groups. 2 of them are bonds, 1 is a lone pair. This will be bent geometry. Again, it doesn't matter if it's single bond or double bond or even triple bond, each of those still count as one electron group. Okay, now let's look at a situation where we have 4 electron groups. So let's clear all of this and add 4 electron groups. As you can see, they'll try to repel each other as much as possible, forming this structure here. So if I can draw that structure, right, this is the central atom. One kind of looks like this, right? It's hard to draw. Well, actually, this might show it much easier. We have this geometry that's called tetrahedral. So as soon as you have 4 electron groups, your electron geometry is going to be tetrahedral. If those 4 electron groups are bonds, you're going to have this tetrahedral structure. It's basically 4 bonds sticking out of that molecule, each at 109.5 degrees apart equally, right? So if we have 4 groups with 4 electrons, it's tetrahedral at this angle. That's the angle between the atoms. If we had, instead of one of those bonds, we had a lone pair, right? We have this sort of geometry here where the electron group geometry is still tetrahedral, right? But one of those bonds is now a lone pair, so there's no atoms to stick out there. So what we have is this sort of triangle pyramid shape. And that's exactly what it's called, trigonal pyramidal, right? It's kind of like a pyramid, with 3 sides. 1 atom up there, 1 there, 1 there, and 1 there. The atom here is the one that's bonded to the others. Trigonal pyramidal. Why there's nothing above it is because that's where the lone pair is, and it's repelling everything. So that's a case where we have 4 electron groups, 3 of them are bonding. We call it trigonal pyramidal. And then again, if you remove one of the electrons and replace it with a lone pair, sorry, one of the bonds and replace it with a lone pair, you'll have a bent structure, right? Just like this V-shaped structure. Remember, these little lobes here with the 2 dots in them, those are lone pairs. There are no bonds there, actually. So we'll have this bent structure. That's why it's called bent. But the angle is different from the bent structure we talked about earlier. So earlier, when we talked about the bent structure, when they had 3 electron groups, that bent structure had an angle of less than 120 degrees. With 4 electron groups, and 4 electron groups with 2 bonds, right? It's also a bent structure, but this time the angle between those bonds are 109.5 degrees. Again, if we increase the electron groups to 5, let's remove everything and add 5 electron groups. This is what it looks like. Let's put 5 bonds instead to make it easier to see. This is what it looks like. 1, 2, 3, 4, 5. We form this sort of structure. If we look at it up and down here, right, it forms a 180 degree angle between these. But the ones in the middle, if we look at from this angle, they're all separated by 120 degrees. So this forms what we call a trigonal bipyramidal structure. Why trigonal bipyramidal? If you think of the middle atom, right, it has 3 atoms coming around it, each around 120 degrees. And then we saw that 2 atoms stick up on the top and the bottom, and this angle here is 90 degrees. So if you think about it, it sets up a pyramid like this, going that way, and then it sets up another pyramid coming down to the bottom. So there's a 3-sided pyramid going up and a 3-sided pyramid going down. So it's trigonal for 3-sided, bipyramidal for 2 pyramids. right? And so that is the electron geometry, which is also the geometry of the molecule if all 5 of those groups were bonds. The angles here, we have 2 different angles because these atoms in the middle that forms part of the plane are 120 degrees separated from each other. But if you look at it from this angle, those atoms are 90 degrees away from the ones in the middle, right? Kind of like that. See, 90 degrees. So that's where we got these 2 angles from. If we remove one of those bonds and replace it with a lone pair, right? So we're in this situation where 5 electron groups, but one of them is a bond, lone pair, so we have 4 bonds. It's what we call a seesaw structure. Why is it a seesaw structure? Because it looks like a seesaw, like this. The lone pair sticking up. These 2 guys are sticking out at 90 degree from the ones in the middle, so they're exactly opposite each other. And then the ones in the middle looks bent with an angle less than 120 degrees. So that's why we have these angles here. If we remove 2 of the bonds so that we have 3 bonds with the 5 groups, let's remove a bond and add a lone pair, we have this T-shaped structure. T-shaped, that's what it's called, T-shaped. And then if we only have 2 bonds but still with 5 electron groups, so let's remove 1 bond and replace it with an electron group, we just have this straight linear molecule, as you can see. There we go, linear. So the angle is 180 degrees. And then finally, we could do this with 6 electron groups. So let's clear everything and put 6 bonds around there. Yep. Everything here is 90 degrees away from everything else. So it looks like this, don't know what you'd call it, but as 6 molecules sticking out, and it forms what we call a octahedral structure. Why octahedral? Well, if you connect all of the white atoms in this model, you'll form an 8-sided figure. So 6 groups, if all 6 are bonds, we form an octahedral structure, and they're all 90 degrees away from each other. If we remove one of those atoms for a bond, we have what we call a square pyramidal structure. Why? Because it's like a pyramid. See, the 4 atoms here forms the base of the pyramid, and this one forms the tip of the pyramid. But in this case, it's a 4-sided pyramid, so it's a square pyramidal. That's what we call it. And then finally, if we had 4 bonds only with the 6 electron groups, again, the whole electron geometry is still octahedral, but let's remove one and add a little electron pair there. We have this flat structure. Again, the bulbs that are sticking up and down here are just electrons, so they don't actually form part of the geometry. We have this flat structure, so it's planar. Plane just means flat. But because there are 4 atoms here, we call it square planar. Square planar. Because if you connect this, you form a square. It's square planar. The angles are 90 degrees. So that's a lot. But these are the various different geometries and angles that you can get from various molecules. So the way to figure this out, exactly which geometry that the molecule has and what are its angles, we need to do a couple of things. We need to figure out how many electron groups they have and how many of those groups are bonding. That's it. So let's do a few for examples, and here are some steps to help you along with that process. The first step you want to do is draw the Lewis structure. Then from that, figure out how many electron groups you have around the atom that you're interested in. Then you determine the number of bonding groups that you have and lone pairs. And then you refer to that table to figure out what their geometry is and what their angles should be. So using those, try to do some of these for practice. Pause the video, and then you can unpause and I'll go over them together. Okay, let's do PCl3, right? So PCl3, I'm going to draw a Lewis structure. I put chlorines at the end because it's more electronegative. Now, to draw the lone pairs and the number of bonds, we also need to figure out how many valence electrons we're dealing with. Phosphorus has 5 valence electrons, and chlorine has 7, and there's 3 of them. So 7 3 is 21 plus 5, that's 26 valence electrons. We already have 6 electrons in these 3 bonds, so we need to distribute 20 electrons. So let's do that. 2, 4, 6, that can't fit anymore. 8, 10, 12, 14, 16, 18, 20. All right, let's make sure our octet rules are satisfied. Chlorine here has 1, 2, 3, 4, 5, 6, 7, 8 electrons, so that's okay, right? The bond is 2 electrons. This chlorine has 8 electrons, this chlorine has 8 electrons, and the phosphorus has 8 electrons. Everybody's happy. So we now need to count the number of electron groups and then the number of bonding groups. Remember, every bond and every electron pair is a group. So here we have 1 group, 2 group, 3 group, 4 groups, right? So 4 groups, we already know the electron structure is going to be tetrahedral. But what is the molecule structure? Well, we look at how many bonding groups we have, and according to this, we have 1, 2, 3 different bonding groups. And so we're looking at, in this table, the situation where we have 4 electron groups, but only 3 of them are bonding. We have a trigonal pyramidal structure. Their angles are going to be about 109, just under 109.5 degrees. If I were to draw this then properly, it would look something like, well, actually I don't have to draw it because I can show you exactly what this would look like. Let's remove all of this. It has 3 bonding groups and a lone pair. So in this case, imagine the purple atom as being phosphorus, the white atoms as being chlorine. This is what that molecule looks like. All right. If you haven't tried 16, 17, and 18, please do so now, and then you can unpause and I'll go it over with you. All right, this is ICl4. So chlorine is more electronegative than iodine, so I'll draw ICl4. And let's count valence electrons. 7 for iodine, 7 for chlorine, and there's 4 of them, and 1 for the negative charge. So that gives us 7 4s 28, plus 7 is 35, plus 1 is 36. We have 4 bonds, so those are 8 electrons. So we're left with 28 electrons remaining. So let's add them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28. All right, so what do we have? We have a filled octet there, so that's okay. Here, that's okay. Here, that's okay. And here, that's okay. Iodine has more than 8 electrons, but we know that's okay. Why? Because it's so far down the periodic table, it can fit more, right? This is one of those exceptions to the octet rule that we talked about. So let's look at how many electrons groups we have around the central atom. We have 1, 2, 3, 4, 5, 6. Let's not make it a double bond. Let's make sure we know that it's a single bond. Okay, so we have 6 electron groups, but only 4 of them are bonds. So let's go to the geometry table. We have 6 electron groups, but only 4 of them are bonds, which means the electron group geometry is octahedral, but the overall geometry of the molecule is square planar. So again, if we're going to do this, we have 4 bonds, 2 lone pairs. This is the geometry of that molecule. Imagine the purple atom as being iodine and the white atoms as being chlorine in this example. So that's what this molecule would look like. All right, let's do another one. Let's do chlorine, nitrogen, oxygen. If you haven't done it, please do it first and then unpause. So we know chlorine and oxygen are more electronegative, so nitrogen will be in the middle. And let's count valence electrons. Chlorine has 7, nitrogen has 5, oxygen has 6. 7 and 5 is 12, plus 6 is 18. But we need to subtract 4 from the 2 bonds, so we're left with 14, if my math is correct. So let's distribute those 14. I'll put them on, well, oxygen and chlorine are fairly equally electronegative, but I'll put them on oxygen first, so that's 6, 8, 10, 12, 14. Okay, so here we have a situation where this chlorine has 8 electrons and that oxygen has 8 electrons, but nitrogen only has 6. So we could potentially have resonance structures coming into play. We could either share these 2 electrons or we could share these 2 electrons. So I'm going to set up both of those cases, and we'll see that the geometry doesn't necessarily change. So if we share these two electrons on the left, we'll get this situation. And then let me draw another one. If we share two electrons, let's say from the right, from the oxygen, we'll have this situation. So let's count the number of electron groups around nitrogen. We have 1 from that, 2, 3. Remember, a double bond or a single bond or a triple bond all counts as one electron group. So we have 3 electron groups in the first situation. In the second situation, we have 1, 2, 3 electron groups as well. So this is a situation where we have 3 electron groups, 2 of them are bonds and 1 is a lone pair. So we scroll up. We have 3 electron groups, but only 2 of them are bonds. So we have, as you would guess, a bent structure. The electronic geometry is trigonal planar, but the overall structure is bent with an angle of less than 120 degrees. If you were to draw that, we have a single bond and a double bond and a lone pair. We have a bent structure of around 120 degrees. All right, let's do the last one. We went too far. Here we go. This complicated molecule, and here they want us to predict the geometry of each interior atom. So interior just means atoms that are not terminal. So let's draw this structure. Carbon, carbon, 3 hydrogens on this carbon, and we're going to put a hydrogen and an oxygen there. Let's count valence electrons. We have 1 from each hydrogen, and there's 3 plus 1, there's 4 hydrogens. There's 4 from the carbons, and there's 2 carbons, and there's 6 from the oxygen. All right, what do we have? 4 plus 8 is 12, plus 6 is 18 electrons. How many bonds do we have? 1, 2, 3, 4, 5, 6 bonds, so that's 12 electrons. So let's minus 12. So that means we need to consider 6 more valence electrons. Well, let's give those to oxygen, because I did not mean to delete my oxygen. We give those 6 to oxygen because it's the most electronegative element here. All right, let's look at octets and duets. Hydrogen has 2 electrons. It can't fit anymore. So all of these hydrogens with 1 bond, that's all I could have. This carbon on the left has 1, 2, 3, 4 bonds, each of 2 electrons. So it has 8 valence electrons. It's okay. The one on the right has 3 bonds, which is only 6 valence electrons. So it needs 2 more. And the only place I could borrow from is that oxygen. So we'll do that. And that's our geometry. Now let's predict what the geometry around each interior atom would be. In this case, the 2 interior atoms are our 2 carbons, right? Everything else is a terminal or end atom. All right, carbon on the left has 4 bonds, no lone pairs. So it's 4 bonds, no lone pairs. So we go here, 4 groups, all 4 are bonds, it's tetrahedral. That's how we learned that. That's how we figured that out. But let's look at the one on the right. So this one, let's use a different color. That is tetrahedral. All right, let's figure out the one on the right. 3 bonds, right? I mean, 4 total bonds because this is a double bond, but a double bond just still counts as 1 bonding group. So 3 bonding groups, no lone pairs. So we scroll up. 3 bonding groups, all 3 no lone pairs. We have a trigonal planar structure. So this would be trigonal planar molecule. So this will bring us to the end of VSEPR theory. In short, in order to figure out the geometries around molecules, we first need to draw their Lewis structure, then count the number of electron groups. Every lone pair is 1 group. Every bond, no matter whether it's double, single, double, or triple, is 1 group. And by figuring out the number of electron groups and how many of them are bonding, we can then figure out the geometry around molecules. And hopefully by now, when you draw these Lewis structures, you can picture in your head sort of what they might look like in 3D space. All right, in our next video, we're going to look at polarity and dipole moment. See you then. Bye.